All right. Welcome back, everybody. This is 15.3. We're looking at conservative vector fields for line integrals. In this section, we just talked about in the last video a conservative field test. And we had df dy equaling dg dx. That was our test. So let's apply some examples. We're going to have some function or some vector function f, where the x component is e to the x cosine y, and the y component is negative e to the x sine y. And we want to know if is this a conservative vector field on some open set. So let's just check it. If we call f the first component e to the x cosine y, and g will be our y component, negative e to the x sine y. df dy is negative e to the x sine y. dg dx is negative e to the x sine y. These do equal each other, so yes, it's conservative. Okay. Just take the partials with respect to them and check to see if they're equal. Let's look at another example. We got a function 3y squared and 6xy. This is a vector function. Is it conservative? And if so, let's find the potential. So if I do df dy, I get 6y. If I do dg dx, I get 6y. They do equal each other, so yes, f is a conservative vector field. Let's find what our phi is. We're basing it off. We did this before in another section. F equals d phi dx, d phi dy. We're going to use that. D phi dx has to equal 3y squared. D phi dy has to equal 6xy. There's a couple ways of doing it. I'll start with, in both cases, I'm starting with our first part. D phi dx has to equal this. So if I integrate it, I'll get phi of xy. And integrating that with respect to x, I get 3xy squared plus gy. Then I can take the derivative of that. So if I take the derivative of that with respect to y, I get 6xy plus the derivative of this with respect to y, so g prime. And that will have to equal our 6xy up here. And we can see that for that to happen, g prime of y has to equal 0. For that right there, g prime has y has to equal 0. So g is not a function of y, so g is just a constant. And our potential function is 3xy squared plus c. Another way of doing it, once you've done this, we can do the same thing, integrate this with respect to y. We integrated this with respect to x. Let's integrate this with respect to y. They should both give us phi, so we'll set them equal to each other. So we already integrated with respect to x. And we integrate the 6xy with respect to y. We get 3xy squared plus h of x. And this up here was 3xy squared plus g of y from up top. We set them equal to each other. We can see the 3xy squared on both sides. We subtract them out. We get h of x equals g of y. A function that is only a function of x equaling to a function that is only a function of y. The only way this works is if neither of them have an x or y in them. They are constant. Okay. Let's take this problem a little bit further. Let's use this in an example. So this is our potential function. We're going to use that on the next page. Let's use the potential function from the last example to evaluate the integral 3y squared dx plus 6xy dy from 1,1 to 4,2. So I can rewrite what we had. F was 3y squared 6xy. And we saw that phi was 3xy squared plus c. Okay. So this is f dot dr when we're using, I already had f written down. Where f is that? And we know the line integral of f dot dr is going to be the potential function evaluated at the second point minus the potential function evaluated at the first point. P1 is 4.2, P0 is 1.1. So let's just do that. V of P1 minus V of P0. V of P1 minus V of P0. This ends up being, this is 48 plus C. Then we have minus 3 plus C. So this just cleans up to 45. Okay. So we can use the potential functions to evaluate problems if we know that it's the potential function for some conservative field. Okay. That's it for that video. We got one more video in this category, this section. It's on the conservation of energy, so some physics stuff. Stay tuned.